Well, I appreciate it.
Did anyone complete it or close to completion?
The first two thumbs done.
Oh, okay. So, what were the problems for the last one?
Describe mathematically.
And
Well, I'm aware of the problem, but what was the challenge in doing it? Just, you have this chart of equations, and there are equations to convert three trigonometric function of sum of arguments into product, right? Or if you add together two trigonometric functions, how to convert it into product, right? So just try practice for getting the standing wave. You're having summation of cosine of one thing plus cosine of another thing, and it depends on both position and time. And you may want to convert it into one figure that will depend only on position, and another that will depend on another trigonometric function only of time. Right? And then you remove time part, take only the spatial part, so that it must be zero. Sine is 0, 0, pi, and pi. Or if it is sine, it will be like pi over 2. And if I get some traps, it can be phase shift. But it's also, you can shift the coordinate axis to select that thing here. It's a general idea, but you can work in details maybe like during So we are starting chapter number 2. I will try to make sure everything before this line is what we did here this year class, and everything which is not covered are recordings from last year. So for some reason you have necessity to join Beltran. So this is your favorite thing, right? So you need to add these two signs together, and there are equations how to convert sum into product. Just try. I'm going to offer next homework within Friday. So there is a little overlap, and I will try to avoid it in the future. So, but we are trying to make maybe a little more relaxed at the end. And here, it's not a secret. I'm giving you heads up. So if you, this will be very complementary to what we're going to do in this chapter. And if you want to prepare for it or look forward to your previous experience and notes, or maybe Wikipedia, look for Fourier transform. So if you are not aware, if you are hearing for the first time, you can just look into Wikipedia if you met it in some type of first and second doesn't apply. So who we are and what are we doing? So we are in physical chemistry class, but we are not doing actual wet lab physical chemistry. We are dealing with characterization of molecules and materials in theory. We are looking for background of things that come out of read on the idea that elements move so quickly that they hold weight nature, and we need some equations that describe it. by now you are masters of reasons that predict the future. You do have prescriptions, which components to add, how to convert the wave function of electron in the past into a function of the electron in the future. And you do have awareness and knowledge of some fundamentals of this theory. So the goal is to predict outcome of instrumental measurement of properties for some real molecules and materials. But we should realize that it is not easy. If it will be so easy, then probably there will be no department of chemistry. There will be only a department of engineering. All problems will be solved. So we are holding this goal, but we are approaching it slowly but surely. And as a first steps, please do not be discouraged, but we will consider some very much oversimplified models. So we will go to practical applications of the skills and fundamental knowledge that we already covered, but it will be, we will not look at the benzene molecule for today or next meeting, and then a couple of weeks from, for a long time. No, we will look for something really oversimplified. You cannot, if you were not taken quantum theory before, you cannot imagine how simple it is. So imagine what can be simpler than a molecule or simpler than
Electron?
Huh?
Just an electron?
Where?
What?
Where?
In a box?
Great. I see your exposure to quantum theory. It's good. Yes, it is favorite and famous problem to practice quantum theory on electron in a box. That's good. But we can be simpler. We can go even simpler. So one ideas that you have implicitly contributed, that we are dealing with, maybe I also try to follow this approximation, we are dealing with only one electron. In fact, there is only one, well, there is hydrogen atom and maybe like lithium doubly ionized lithium, where an atom has only one electron. In all other systems, there are abundance of them, and electrons can collide with each other. We will not cover in this course how electrons interact with each other. So we will try to avoid their collision as much as possible and just look how electrons respond to the external field, which can be field of attractive ions. Attractive, not that they're so pretty, but they're attractive electrons. And maybe something oversimplified models like Fox. But I did ask the question, one electron where? Why did I ask? There is a fundamental reason. So where, not where, but electron in which environment? So to practice the equations that we went through, one needs to know operator of energy. It consists of potential and kinetic. And potential energy is literally who attracts my electron or who repels it. So it's potential profile. And it depending on where we place our electron, the potential energy will be different. Okay? Now, question not for the knowledge. What is the simplest potential?
No.
Yes, exactly. So simplest potential is absence of potential. Okay? So Hamiltonian, where we do not have kinetic energy, or we always have, where we do have kinetic and have no potential. So in which circumstances we experience no potential energy there. Our poor electron experiences no potential energy.
In free space?
Yes, in space. So we will be space explorers from now on. Free space. Well, of course, to survive the mathematical hardness of these problems, we will not go into true three-dimensional space. We will go into one-dimensional space. It's one-dimensional space which has only one element. So it will be, imagine, well, say, imaginary and fantasy, science fiction, a world, a universe that contains only one electron. There are no other objects, no planets, no stars, no ions, no other electrons, just one electron is traveling in a free space. Okay? But we are going to put some mathematical foundations and get comfortable with predicting what this electron can do. And it will be not super trivial. There will be some fine things. Okay? So this will be, I don't know, for 3 meetings, at least, maybe more. It's, we will solve this problem with all, well, not all, but substantial amount of rigor. And then we will try to keep the same level for other problems. That's the stuff that you know, right? Ways to predict future. I'm just focusing on that. So the last way that we learned last time is that we think that the past initial condition for wave function at time 0 at all points of space, there is a protocol to get it in the future, right? And we need to find eigenfunctions, eigenenergies, and we need to find projections of the initial condition onto the eigenfunctions, right? Nothing we did last time. So the mini goal, the mini purpose, mini aim that we pursue is to see how can we practice this protocol for electron in free space. So we will use our scientific intuition to guess for initial condition, and then we use this protocol to predict future. Do you agree that it is boring? Maybe helpful, but somewhat boring. So before we go to mathematical details, we may want to set up the scientific goals. Like, are we going to learn something new out of this exercise? So we need to have something pleasant and interesting. Otherwise, there is no reward and no pressure that will make us to invest 3 meetings to do it. So what are your intuitive expectations? What electron in free space?
Move
Yes. How?
in a wave.
Huh?
In a wave.
In?
You say like a wave?
Oh yes, it is a wave. We since no one was protesting against equations, now it is accepted. Yes, it will be a wave. But there is a trivial solution. When we can just take our electronic wave and spread it over infinite space, so that it will not move. It will just occupy everything with a very little probability density. It will be somewhat boring. and hard to find practical connections. It would be more interesting if we, for example, take hydrogen atom and then suddenly steal the proton, so that electron doesn't notice it. I'm not teaching you anything bad. It's just only thought. Well, there are some more respectful ways to consider localized electrons. Maybe electronic gun that injects electron in some localized space. But if we know that electron can be at one point, it's always distributed, but we can make it like semi-local. We can have it distributed around vicinity of some point. Like if it was S state of electron and hydrogen atom, where we store the proton, at initial time it will be holding the same space, right? Maximum near the place where former ion was staying, and less as you go away. And then we can step aside and see what would happen. So, any ideas?
You just took the electron away? I mean,
If
the proton
you
away?
took proton away, yes. So proton was holding electron distribution near the center because it was attractive. Now we remove this attraction center. What would happen?
Just kind of like go anywhere. And like, are we still saying like it's in a box?
No box, infinite space. Will it go anywhere like this little cloud, go left or right, or it would like equivalently scatter in both directions? Yes. So it will.
Just a big sphere.
Yes, it will get lower and lower. Next one is the wrong word. Concentration. Lower and lower density in each vicinity. So it was localized, and then it will start delocalized, spreading out. If I take maybe padding or shower gel, try to make a fire, it will not hold for a long time. Start to spread. It's invention of last second. I never heard a comparison for that. What if our original hydrogen atom, before we have stolen the proton, was moving, was having non-zero velocity? Means the electronic distribution was also moving. Okay? Now we steal the proton. What would happen with this distribution? Would it suddenly stop?
Won't the cloud just keep expanding?
It's keep expanding, but where the center of the cloud will be? It keeps moving. Yes. So without any boring math, you already have. You cannot call it answer, but you can call it educated guess, scientific hypothesis that localized electronic cloud will continue to move according to initial average velocity, and the width of this distribution will continue to increase. Okay? So there are two statements that hypothetical statements that we want to prove right or wrong. So it's our scientific formulation. And our methodology, our tool to address this scientific question will be to practice the expansion of initial state over eigenstate. Well, there are several unknown things, but we will make them known. We will go through it. So I do not have slide on it, but you may summarize what is our goal, so that if you have a general idea what we're doing. I can try. How to steal a proton? is localized distribution of a function will A move according to momentum, initial momentum, and B will increase with okay. Which money are used in Europe? Huh?
The euro.
Since when?
That would be,
What were the money in Germany before that?
Frank.
no,
In France.
marks.
Uh-huh. So, which pictures are shown on American currency?
Presidents.
Presidents.
Benjamin.
So, who were shown on German currency?
And like mathematicians and stuff like that.
Right.
Scientists.
Yes. Yes. German marks. Gauss, and you're aware of Gaussian function, right? There were no Nobel Prize at the time when he was alive, therefore he didn't do it. So it's what one can put on mind: portraits of scientists, equations, and curvatures. And probably the best familiarity with Gaussian distribution is when in freshman quarters one is getting grading on a curve, right? By some reason, in a large amount of large classes, why don't we assume something similar between large classes and electrons? Electron can be localized also according to Gaussian. It's not that we love these functions so much, but it is hard to design a function that will correspond to localization of something in the vicinity of something. It's just good mathematical equation for shape, right? So it is exponential with minus square function in the power, right? This could be a good guess for a stolen proton, for electron that is localized in the vicinity. We need initial condition, we need initial distribution of electrons. And you can assume also as our hypothesis number 3. At time 0, our wave function has a Gaussian shape. One cannot do everything according to the rules and rigorously. One needs to use scientific intuition and guess something. Or x times 0. There is a factor, there is a
2 if it's
So we'll start to believe that our electron was localized in this simple X. So this is summary of one of our common hypotheses, that if we can process this distribution with 2 parameters, with average position x0, we can assume that this, if we are away from time 0, it will be not x0 but x depending on t. At time equals 0, it will be at 0, and then it may shift somewhere. And one of our hypotheses is that the center of the distribution will continue motion according to initial velocity, right? So if you know the momentum divided by mass velocity of this distribution, we can tell that the position will be initial position plus this velocity times time passed since beginning of the experiment, right? So if you can get such equation as an answer of mathematical exercises, if you will find it, we will be okay. If anyone can be happy, we will look at mathematical equations. Else? So we can sketch a plan how to address, how to prove our hypothesis right or wrong, how we can practice our third way to predict the future in application to fantasy universe with single electron in one dimension. I hope it was not protested against boring nature. So we do need to solve time-independent Schrödinger equation to get the eigenfunctions and eigenenergies, right? And we are going to practice. So this is kind of clear, and it goes along with what we discussed before. So this part is literally reproduction of what we did on Monday in class. And in order to practice this schedule, we need to throw in the initial condition, which is our free rules design. Initial condition, which will be Gaussian. And as a last step, you will need to make a convolution between eigenstates of Hamiltonian and initial condition. Do not feel irritation, do not protest, I'll come to this again. In order to practice third way to predict future, we need to project initial condition onto eigenstates, right? Multiply initial condition times eigenfunction and make integration to get this C sub k coefficient, right? So we will do it. Our initial condition will be Gaussian function. So before we go through this plan, we will need to formulate Hamiltonian that doesn't have potential energy, only kinetic energy. And this will be really easy. So the whole path will be doable and easy if we introduce and discuss concepts of plane wave, which we kind of touched before, right? And momentum operator, which is the only equation that we need to use. All others can be done. What is a plane wave? And why plane wave is plane?
Would it be a wave that exists solely on a two-dimensional plane?
I see logic in your guess. plane wave is best defined in three dimensions, but we are going to apply it to one dimension. Why this plane wave? And you may have heard about this concept in other courses, or you will, especially if you will take electricity in physics, which maybe you are not looking for, but it is a part there. So if you have a like electromagnetic wave, radio wave propagating from the cell phone to the antenna, you have oscillations of electric field up and down, and it goes with the same phase, same value of this electric field at a plane. It propagates forward and then it changes. So there is a who was not throwing stones in the water? Everyone did, right? What do you see?
Rivers.
What are the shapes of them? So it will be a circular wave. So if you have one wave distributing, departing from point where of you're aiming, where you placed your stone, it will be like wave of the same shape, distributing away and keeping the same shape at a given distance from the center. So it will be circular. If you make atomic bomb explosion in space, everything will be distributed in a spherical way from the point of explosion. So the front of a shock wave, will distribute as a sphere. But if we are very far away from the emitting center, then the spherical wave can be considered as a just chunk of a little plane. So plane wave is because it is a region of space of the same phase, where the wavy shape keeps the same shape at each point on this plane. Plane wave, if it just distributes, or wave front is given. If we are speaking about one-dimensional relative, we do not have planes. Instead of like for three-dimensional space, plane wave is in 2 dimensions. For 2-dimensional space, plane wave for this plane wave will be a line, 1 dimension. For 1-dimensional space, area of the same phase will be a point, a traveling point. If you have the running wave, you just sit on the top of a hump and observe how you travel. So it will be like, instead of plane, it will be just a point. But what is called plane wave is we think that we already agreed to do this. So it is an exponential wave because we know that nature of electronic wave function gets to between real and imaginary part. It needs to be complex. Therefore, instead of sine and cosine, we do exponential. And in the argument, we have both space and time accumulation of phase, right? In more, so it is a general solution for wave function. in a more narrow sense, one can call plane waves the same equation without spatial part. So it is so it is a set of fringes of the same amplitude distributed equivalently among all space from plus to minus infinity.
It's in the way, so it's a plus or minus I to the sine px over h. So when it says cosine px over h bar, is it plus or minus I again?
I understand your question. I understand where it comes from. And the answer is very no. Why? Because momentum can be oriented left or right. So it's a question of convention. We can agree it's minus one. But later on, we will make integration over different values of momentum. We will add together plane waves corresponding to different wavelengths, different momentum, different density of fringes. And we will consider both positive and negative momentum. So if we have it only positive or only negative, we will not reproduce all multitude of phenomena. We need to agree that the wave can travel in opposite directions. Good. What is this square root of n? It's declaration of my reasons. So I do not want to go into details, and therefore I cannot request it from you. Anytime you write a wave function, you may want to assume and believe and hope that it is orthogonal and orthonormal. So if you multiply two wave functions and integrate, you get either 0 or 1. So sometimes through procedure of numerical or analytical solution, you can get more than one. And it will be bad, then all our theorems will fail. So we always need to do so-called normalization procedure to divide wave function by such number so that upon practicing orthogonalization procedure, we will get either 0 or 1. And this is the normalization factor that will make sure that it is maintained. In some problems, we will literally find this factor. In most cases, it is constant. In some crazy cases, it changes with either time or space. But if you tell normalization in public on some exam, no one will tell that you are wrong. Okay, so plane wave. The large momentum means there are dense fringes. Low momentum means there are sparse. Okay. I'm going to go not forward but backwards to check if I'm dealing well with okay, plane wave concept. Now I need to go to momentum already. We got through it. It is what we were discussing, that if you localize it at the beginning, then it will start to expand. Okay, we need momentum operator. What is it? Am I right or wrong? I want to be with the time for that. But please try to catch me on errors, and I will try to make notice and give you credits. So to beneficial both to them. I will not. I promise not to make intentional mistakes. So it's for real. So momentum operator is derivative over space. Anyone has protest against it, or when we discussed it up last week, it was okay. So through this ideas of accumulation phase, we guessed that there is an exponential this momentum power. If you want to extract momentum out of such exponential, you need to take derivative over space. Then you really want to take care of particles. So I'm going to repeat in once again a thing that I was doing about a week ago. So we do have momentum, and we have a frame flow. If I was wrong with this minus, you discovered it. So let's practice applying the plane wave. What happens if you repeat like minus bar ddx so all factors go to the front. Derivative of exponential is the same exponential, and everything except independent variable goes as another factor at the front, minus I p over h bar. Right? No everything calculated. Yeah. Okay, now we do have a couple of cancellations. So h bar cancels. Minus times minus will be plus 1. And I times I will be minus 1. Minus 1 over e plus x divided by a. So probably I was it was not best idea to put minus. If you would put plus right away, you don't see it here. Then we wouldn't have minus in there. But what we see, I'm not going to correct this right now. But what we do see that it will we will reproduce the sign minus p stays here. P minus p times wave function itself. Do you see it? No? So this p with hat acting on the plane wave is just a derivative with some taken care of factors. And if we cancel factors and combine them together, we can recognize that it will be the same function. So here is how we define it, and here what we got upon applying the operator to this function. Oh, yes. So applying operator P is we get value of the momentum, so without head, times the same function. And this minus sign is just my punishment for having minus here. I do not want to go quickly and remove it, otherwise it will be too much mess. But acting by momentum operator on a plane wave, you are reproducing the plane wave again. This value of momentum on the front. How do we verbally represent it? How do we describe it? Momentum operator and plane wave functions are in relations. The plane wave function is an eigenfunction of momentum operator. So this is an example of eigenvalue problem. So it is not the time-independent Schrödinger equation. It is not for Hamiltonian, but it is similar mathematical nature of a problem. So if we here we did reverse engineering. We plugged in solution and function and suddenly found that it is solution. But formally, one could start from making this as an initial question: like, which wave function would be eigenstate of this operator? And the answer is any plane wave. Any plane wave is eigenfunction of momentum operator. Momentum operator. Okay. This is what we are going to get at the end of the week. And here is a repetition, once again, of our plan. So we are going to plug in wave functions and energies, and we are going to find expansion coefficients. I think time is, there are 2 minutes more, but it will be not right to rush. We better prepare ourselves to do it slowly but surely next time. So once again, where we are and what are we doing? We are checking the hypothesis that hydrogen atom with stolen proton will keep moving forward and expanding. Therefore, we guessing Gaussian wave function as initial condition. And in order to practice third wave in the future, we are pumping our mathematical muscles by concepts of plane wave and which operator? Moment. So when we meet next time in class on Friday, we will try to solve time-independent Schrödinger equation for space and plug things into the third way to predict future. This evening, I will help to whoever needs help with homework number 1, and we will continue getting over basic skills of using MATLAB software. It will be needed. You will see how hard some mathematical problems is, and we will solve them with computational tools. One far goal and close goal. In about 2 weeks, we will make another set of presentations where we will split all basic skills of operating MATLAB software, and you one by one will present. And now, evenings we prepare this. Let me come to this slide. Yes. Meeting is done, dismissed. See you at 5.
Leave over here and you